Deep beneath our feet, far beyond the deepest mines, volcanoes, and even the tallest mountains, lies a world that humans can never directly reach. This hidden world is Earth's interior. For many years, scientists believed that Earth's deepest layer, the core, was almost completely sealed off from the rest of the planet. According to this old view, once heavy metals like gold sank into the core billions of years ago, they stayed there forever. However, a new scientific study has changed this idea in a surprising way. Researchers have now found strong evidence that Earth's core is not entirely isolated. Instead, tiny amounts of precious metals, including gold, are slowly leaking upward from the core, passing through the mantle and eventually contributing to the material found in volcanic rocks at the surface. This discovery does not mean that gold will suddenly become easy to mine or that treasure will start flowing from volcanoes. What it does mean is something much deeper and more important. Earth is more dynamic and interconnected than scientists once thought. The planet is still slowly mixing itself from the inside out, even after more than 4 billion years of existence. To understand this discovery, it helps to first understand how Earth is built. Earth is not a solid ball of rock. Instead, it is made of layers, each with different properties and compositions. The outermost layer is the crust, which is where humans live. This layer is very thin compared to the rest of the planet. Beneath the crust lies the mantle, a thick layer of hot, slowly moving rock. The mantle makes up most of Earth's volume. At the center is the core, which is divided into a liquid outer core and a solid inner core. The core is extremely hot and rich in metals, especially iron and nickel. Scientists estimate that more than 99% of Earth's gold is locked inside this metallic core. If all the gold in the core were spread evenly across Earth's surface, it would form a thick layer covering all the land. For decades, scientists assumed that this gold was permanently trapped. The new research shows that this assumption was not entirely correct. To understand why gold is mostly in the core, we need to go back to the early days of Earth's formation. When Earth was young, it was extremely hot, so hot that much of it was molten. During this time, heavy elements like iron, nickel, and gold sank toward the center in a process known as the iron catastrophe. Lighter materials floated upward, forming the mantle and crust. This process happened very early, within the first tens of millions of years of Earth's existence. Afterward, meteorites continued to bombard Earth, adding more metals to the crust. Because of this history, scientists believe that almost all the gold from Earth's original material was locked away in the core, while the gold we mine today mostly came from later meteor impacts. Separating these two sources, core gold and space gold, has been one of the hardest challenges in geology. The new findings come from researchers at University of Göttingen. Their study was published in Nature, one of the world's most respected scientific journals. The research was led by geochemists Nils Messling and Matthias Wilbold. Instead of looking for gold directly, the scientists studied a different metal, ruthenium. Ruthenium is extremely rare in Earth's mantle and crust because, like gold, it strongly prefers to sink into the core. What makes ruthenium special is that it has slightly different versions called isotopes. These isotopes act like fingerprints, allowing scientists to trace where the metal came from. Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. This small difference gives isotopes slightly different physical properties. In most cases, isotopes are mixed so evenly that they are impossible to tell apart. However, in Earth's core, the isotopic makeup of some elements is slightly different from that found in the mantle and crust. These differences are extremely small, but with modern technology, scientists can now detect them. Ruthenium isotopes are especially useful because almost all ruthenium moved into the core when Earth formed. That means any unusual ruthenium found in mantle rocks is a strong clue that it came from the core. To find these clues, the researchers studied volcanic rocks from Hawaii. Hawaii is not located at the edge of a tectonic plate like most volcanoes. Instead, it sits above a mantle plume, a column of hot material rising from deep within the Earth. Mantle plumes act like natural elevators, carrying material from the deepest parts of the mantle up to the surface. Because of this, volcanoes like those in Hawaii provide rare samples of Earth's interior. When the Göttingen team analyzed Hawaiian lava, they found something remarkable: elevated levels of a ruthenium isotope called ruthenium-100. This isotope is strongly associated with Earth's core and is not normally found in such high amounts in mantle rocks. The presence of this core-like ruthenium isotope cannot be easily explained by other sources. Recycled crust meteorite remnants or surface contamination do not match the isotope patterns seen in the Hawaiian samples. The only explanation that fits all the evidence is that a small amount of material from Earth's core has mixed into the mantle. Over time, this material traveled upward with mantle plumes and eventually erupted as lava at the surface. Scientists estimate that less than 0.25% of core material mixing into mantle rock is enough to produce the isotope signals observed. This tiny amount is almost nothing in practical terms, but scientifically, it is enormously important. Ruthenium was the key tracer in this study, but it is not the only metal involved. Other precious metals, such as gold, platinum, palladium, and rhodium, behave similarly under extreme conditions. If ruthenium can leak from the core into the mantle, then these other metals can too. This does not mean they suddenly become concentrated or easy to extract. The process is incredibly slow, taking hundreds of millions or even billions of years. What it shows is that Earth's core is not a sealed vault. Instead, it is slowly exchanging material with the mantle above it. The boundary between the core and mantle is one of the most extreme environments in the planet. Temperatures there can exceed 3,000 degrees Celsius, and pressures are unimaginably high. At this boundary, small amounts of metallic material from the outer core can interact with superheated mantle rock. Over long periods, this interaction allows tiny quantities of core material to become mixed into the mantle. Once mixed, this material can be carried upward by mantle plumes. These plumes rise slowly but steadily, eventually feeding volcanoes at the surface. Ruthenium is not the only isotope that supports this idea. Scientists have also found unusual isotopes of tungsten and high ratios of helium-3 in some volcanic rocks. Helium-3 is extremely rare at Earth's surface, but is thought to be common in deep, ancient reservoirs. When helium-3 appears alongside core-like tungsten and ruthenium signals, it strengthens the case that the material came from deep within the planet. These combined signals paint a consistent picture. Some mantle plumes originate near the core mantle boundary and carry chemical fingerprints from Earth's deepest regions. Not all volcanic regions show signs of core material. The strongest signal was found in Hawaii, while other hotspots showed weaker or no signs at all. This suggests that only certain mantle plumes tap into regions near the core mantle boundary where this mixing occurs. Earth's interior is not uniform, and different plumes sample different source regions. This uneven sampling helps explain why the signal is rare and difficult to detect. It is important to be clear about what this discovery does not mean. It does not mean that volcanoes will start producing gold-rich lava or that mining companies can tap into Earth's core. The amounts involved are far too small and too spread out to be useful economically. The real value of this discovery is scientific. It changes how scientists understand Earth's evolution, internal mixing, and long-term behavior. It also helps researchers build better models of how rocky planets form and change over time. Earth is not the only rocky planet in the universe. By understanding how Earth's core and mantle interact, scientists gain insight into how other planets might behave. This research helps answer big questions about planetary cooling, magnetic fields, volcanic activity, and the long-term survival of atmospheres. It also shows that planets can remain chemically active deep inside for billions of years. In simple terms, this study reveals that Earth is still alive on the inside. The planet is not frozen in its early history, but continues to evolve, mix, and change. Gold and other precious metals are not just surface treasures. They are part of a slow, deep cycle that connects Earth's core, mantle, and crust. Even though the process is incredibly slow and subtle, it reminds us that Earth is a dynamic system, one that still has secrets waiting to be uncovered. This discovery is a powerful example of how modern science can uncover hidden processes deep within our planet. By studying tiny isotopic differences in volcanic rocks, scientists have revealed a connection between Earth's deepest core and its surface. While this will not change daily life or create new sources of wealth, it fundamentally reshapes how we understand Earth's interior. It shows that the planet is more interconnected, more active, and more complex than we once believed. In the end, the true treasure is not the gold itself, but the knowledge gained about the incredible world beneath our feet.